Okay, so this reading quiz is all about the meaning of integrals. You'll see plenty of AP questions relating to using integrals and accumulation integrals in particular to find the total amount of some thing that you're dealing with. So let's take a look. What is accumulation? We talked about this towards the end of the semester last year, and we talked about an accumulation integral when we were doing all those FTC problems. And one statement that we mentioned was that the integral of a rate of change gives our net change. In fact, we call this the rule of net change. So now it's time to actually put this statement into action. When we integrate a rate over a particular interval, we get net change. So priority number one is to look back at kinematics, which was the study of objects in motion. And we dealt with three particular terms when we were dealing with kinematics: our position, our velocity, and our acceleration. If you'll remember, and you look at the chart there, the derivative of our position, which oftentimes we'll call s of t, it could be x of t or y of t, the derivative of our position function is velocity. Well, if you look over to the antiderivative part, it should follow that the antiderivative of velocity is position, s of t, plus our initial condition, c, our constant of integration, rather. Similarly, our derivative of velocity was acceleration, so our integral of acceleration should be velocity plus c. For example units, we might have our position measured in meters, which would mean our velocity is measured in meters per second, and our acceleration would be measured in meters per second squared. If you notice, as you move up the table there, you lose one of your time units. For example, when you're going from acceleration in meters per second squared up to velocity, you go up to the units of meters per second. A couple of new formulas for us. If you remember, way back in about October, we talked about the displacement of an object. And if you'll remember, displacement was the net change in position. One way that you can write this is s of b minus s of a, which in this case a and b would be our initial and final positions respectively. Well, now we can tie that into integrals. The integral from a to b of v of t dt is s of b minus s of a because s, or position, is the antiderivative of velocity. Similarly, we can come up with a formula for distance. And with distance, all we need to do is remember that we're going to integrate speed, which would be the absolute value of velocity. We want to make any backwards movement into positive. If you remember when we talked about distance initially, we talked about saying that if we move backwards, we still count that as positive movement because we're still moving a distance. So what is the difference between these two formulas? Well, you'll notice that the formula for displacement's integral has no absolute value, while the formula for distance's integral has an absolute value. How does the plus c come into play? Well, we're going to be using the term initial condition quite frequently by using the statement derived from the FTC. If you remember, we talked about the magic carpet. In other words, if we want to find our position at B, we need to take our initial position at A and add the integral from A to B of f of x dx. So our function's position at B is determined by our starting position and how much we've accumulated in between. That's the whole net change philosophy phenomena. So here's an example. This will take 2 slides to do this. So suppose that v of t is equal to 3t minus 5 for a particle traveling along the x-axis, defined only from 0 to 3. Suppose also that the initial position of the particle is the position s of 0 is equal to 7. Find s of t for any time t. Well, we're given velocity. We can integrate velocity to find our position. So that's what we'll do. If we notice, when we integrate our velocity function, which is 3t minus 5 dt, we're going to get 3t squared over 2 minus 5t plus c. That's just a simple antiderivative. However, since we're given a specific initial position, we need to solve for the specific antiderivative that satisfies that condition by finding our c value. So this is accomplished by plugging in our time 0 and our position 7. So at time 0, our position is 7. we plug in 0, we find our c is equal to 7. Thus, our formula for position is s sub t is equal to 3t squared over 2 minus 5t plus 7. Question 2. Find the total displacement and distance for the particle traveled on the time interval, in this case 0 to 3. Well, our displacement would be the integral from 0 to 3 of v of t dt. We already found our antiderivative, which was 3t squared minus 5t plus 7. All we need to do is plug in times 3 and times 0 and subtract the two of them. Our distance is the integral from 0 to 3 of the absolute value of v of t dt. Now I'm going to show you how to solve this not using your calculator, but you also need to keep in mind that you generally will have your calculator available for these. If you remember back on the first slide, our function was v of t is equal to 3t minus 5. v of t is equal to 0 at 5/3. And you'll notice that the particle, the velocity of that particle will go from negative to positive at time 5/3. And so what we're going to do, just like we did in previous problems, is we're going to break up our integral from 0 to 5/3 and from 5/3 to 3, because that's where the particle changes from negative to positive velocity. In doing so, we're going to evaluate each of these integrals separately and make any displacement between the time period 0 and 5/3 and from 5/3 to 3 into positive values. So just as we did with the displacement, we want to find our displacement from 0 to 5/3, make that into positive distance, and find our displacement from 5/3 to 3 and make that into positive distance. I saved a lot of work and steps on here. When you evaluate it, you end up with 41/6. The reason, again, that we choose 5/3 as a breaking point is because that's where v of t is equal to 0. Our calculator will verify our answer, and again, you most often have your calculator to solve distance problems such as these. A second example. The velocity of a car is recorded at half-second intervals in feet per second. Use a trapezoidal sum with n equals to 8 trapezoids to approximate the integral from 0 to 4 of v of t dt, and explain the meaning of the integral in the context of the problem. So you'll notice that we have even intervals in this case. We have intervals from 0 to 0.5, 0.5 to 1. All of these intervals that we're giving in the chart have width of 0.5, and those would be the width of our trapezoids. This will allow us to use our trapezoidal rule from our previous reading. When you're using a chart, make sure that you cite the chart by explaining that you're using v of 0, v of 0.5, v of 1, etc., and then go on to a second line to show that you've actually plugged in the values. This is part of the work points. I have a v of 3.4 on the work there. Please ignore that. That should be a v of 3.5. When you work it out, you use your trapezoidal rule, you end up with 112.5 feet. As we'll see in a later slide, we're going to follow the principles of tau when we're explaining our integrals, just like we did with explaining our derivatives. Tau stands for time, amount, and units. So when we're asked to explain the meaning of this integral, we look at our time. In this case, we are finding the first 4 seconds for whatever amount we're trying to find. In this case, the amount is total distance traveled, which is 112.5, and we want to include our units, feet. So altogether, our integral set means the total distance traveled, which is 112.5 feet during the first 4 seconds. If you can remember how to do a sentence like that, you're going to get plenty of free points, nice, easy points on the AP exam. Example 3 is a borrowed AP question. It says, 2 runners, A and B, run on a straight track from 0 to 10 seconds. The graph below, which consists of 2 line segments, shows the velocity in meters per second of runner A. The velocity in meters per second of runner B is given by the function v of t is equal to 24t over 2t plus 3. Find the total distance run by runner A and the total distance run by runner B over the time interval 0 to 10 seconds. Indicate units of measure. So again, we want to find total distance. Total distance, as you see in the integral for setup for runner B, is the integral from 0 to 10 of the absolute value of v of t dt. All we need to do for both runners is find the value of the integral. In this case, though, because you have a graph for runner A, you're going to find that integral differently than we would find the integral for runner B. For runner B, we just need to use our calculator. We're going to integrate from 0 to 10 of the absolute value of V of t dt. When we do so, we get 83.336 meters. When we integrate for runner A, we notice that we have two shapes that are very convenient. We have the shape of a triangle, whose height is 10 and whose width is 3. And we have the shape of a rectangle, whose width is 7 and whose height is 10. When we find the areas of those two shapes, we end up with 85 meters. So now, back to the net change theorem. Again, the statement is, if you integrate a rate of change in an interval, you get accumulation, or a net change. For example, when we integrated our velocity, we got our net change in position. We can apply that to other rates of change, not just velocities. And the statement that you'll want to remember is that f of b is equal to f of a plus the integral from a to b of f of x dx. The integral represents our net change, which we're going to add to our initial condition. The net change is like our magic carpet, which carries us to our final condition, current condition. So here's a fourth example of that. Suppose water flows out of a tank at a rate of 400 minus 4t liters per minute. Explain the meaning of and find the value of the integral from 0 to 10 of r of t dt. Again, your responses should follow the principles of tau. T, time, list whatever interval you're dealing with. A, amount, talk about the amount. U, units, include the correct units. In this case, the integral from 0 to 10 of r of t dt can be evaluated with a simple antiderivative in the FTC. The antiderivative is, in fact, 400t minus 2t squared. Please ignore the typo on that. From 0 to 10 of 3,800, which gives you the answer of 3,800 liters. This integral represents the total amount through to 3,800 liters that will flow out of the tank from minute 0 to minute 10. So the amount, 3,800, the units, liters, that flows out of the tank, be very specific about what's going on with that, from our minute 0 to our minute 10. You can say in the first 10 minutes, it is not acceptable to say in 10 minutes, because that could mean any 10-minute interval. Example 6. On a typical day, a city consumes water at the rate of 100 plus 72t minus 3t squared, measured in thousands of gallons per hour, where t is the number of hours past midnight. What is the daily water consumption? First question. And how much water is consumed between 6 p.m. and midnight? Second question. To answer our first question, we can go to our calculator. We're going to integrate from 0 to 24 of r of t dt. That is our rate of change. When we integrate our rate of change, we get an accumulation of the number of thousands of gallons. In fact, the number of thousands of gallons is 9,312, which I simplified to say 9.312 million gallons. We do the same to talk about the water consumed between 6 p.m. and midnight. Keep in mind that 6 p.m. is 18 hours past midnight, and we're talking about midnight of the next day, which would be hour 24. When we integrate that, we get 1.680 million gallons. So how would we use tau, for example, with the second integral? We would say that the integral tells us that 1.680 million gallons, or 1,680,000 gallons, have been consumed from time 18 to time 24, or from 6 p.m. to midnight. Finally, example 7. The rate in liters per minute at which water drains from a tank is recorded at half-minute intervals. Use the average of left and right endpoint approximations to estimate the total amount of water drained during the first 3 minutes. Now, we talked about this when we did the trapezoidal rule reading quiz, which is reading quiz 2. The trapezoidal sum is just the average of our left and our right endpoint approximations, as long as our base lengths are the same and we don't have unusual widths for our trapezoids. So all we need to do is we need to do the trapezoidal sum, or we could write out what our trapezoid areas are. Notice I'm citing my chart. In this case, I write r of 0, r of 0.5, r of 1, r of 1.5, and so forth. Our middle values are counted twice. Our end values are counted one time. We plug in our values. We calculate, we get 132 liters altogether. So tau would tell us that in the time period, or the first 3 minutes, the accumulation of water draining from the tank would be 132 liters.